Now that we've talked about exponential growth, we are going to be moving on to exponential decay. So, as I'm sure you have thought from the title, exponential decay is the opposite of growth. So, it's when something is losing or when something is decreasing. Some real life examples of this are carbon dating, which we will be doing an example of later, as well as the value of something over time. So, for example, a car's worth over time. If you know the initial amount and the decay rate, you can use the following model. Now, what you're going to notice about this model is that it looks almost exactly the same as our last formula in exponential growth, except there's now a minus. Now, that probably makes sense since we already said that exponential decay is a decrease or a losing every single time. One important fact before we move on, when you are solving these problems, and you probably ran into this in the last chapter, your rates need to not only be represented as a decimal, we talked about that, but they need to match the number of compounding periods. So for example, if something is increasing or decreasing by 20% per week, you need to make sure that you're plugging in weeks for your n value. So if they wanted to know how much was going to be left in, say, 14 days, you would be plugging in a 2 because 14 days is 2 weeks. We're going to start in with an example. So the population of a small mining town was 13,700 in the year 2000. Each year, the population decreases by an average of 5%. A. Explain why the situation described is an example of exponential decay. So looking at this right away, we know that this is an example of exponential decay because it's decreasing by 5% per year. Now this means that it's not decreasing by 500 people per year. That would be linear if it decreased by the same amount per year. But since it's decreasing by a percentage each year, we know that that would be exponential. Our next step is to write an equation to model the situation. So the first thing that we're going to do is write our formula. So P of n is equal to P naught 1 minus r to the exponent n. And when I plug in all of my information, I know that my initial value is 13,700. The year is a little bit interesting. So this 2000 is going to be my base year. And then my rate is 5%. So when I'm writing this in, I'm going to get 13,700. 1 minus 5% as a decimal is 5 divided by 100, or 0.05. And then we're going to put it to the exponent n. Now I am going to leave a little note for you down here where we say n is the number of years since 2000. And you're going to see why that's important in just 1 minute. Now going back here, I'm just going to finish this off. 13,700. 1 minus 0.05 is 0.95. So I'll just tidy this up a little bit. So I've just went ahead and recopied our equation because I moved to a different page for more room. Part C says, what will the population be in the year 2005? Now I'm going to go ahead and plug in some numbers here, but I am not going to plug in 2005. If you remember, we said that n is the year 2000. That's our base year. So what we're actually plugging in is 5 because it's only been 5 years since that base year. So we're going to take P of 5 and we're going to plug a 5 in wherever we see an n. And so I'm going to be getting 13,700 times 0.95 to the 5. Now again, most of you will probably have to do the exponent first on your calculator before multiplying by the 13,700, but either way you need to be able to get an answer of 10,600.8, which we could really just leave off and leave it as 10,600. In the last part of this example, it says that we need to use our equation to estimate when the population will drop below 5,000. Now, what I'm knowing this time is that it's not giving me an n. I am actually getting a final population, so I'm getting this P of n, and I'm asked to solve for my exponent. So I'm going to plug that 5,000 in, and I'm going to leave everything else the exact same. Now notice how it says estimate. You don't know how to solve this equation, and you actually won't learn this in high school. Why it says estimate is because we're going to be using a kind of a guess and check. So in order to solve this equation, we're trying to get n by itself. We're going to go ahead and we're going to divide both sides by 13,700. That's going to leave us just a 0.95 to the exponent n on the right. And on the left, when we do 5,000 divided by 13,700, we get 0.36. Now I'm going to go ahead and just start by, picking a random number. Honestly, I'm going to just pick 10. So if I plug a 10 in here and I do 0.95 to the 10, I get 0.5987. Now that, I'm looking for 0.36, so this is way too high, okay? This means that my population is still too high. I'm not even close to that 5,000. I'm going to go ahead and I'm going to try 15. So 0.95 to the power of 15, and I'm going to get a 0.46. Now this is better, but it's still too high. I'm going to try 20. So 0.95 to the power 20, and I'm going to get 0.358. This is super close. It's maybe a little bit too low, not too bad at all. I'm going to go ahead and just try 19 to see what my answer is when I do 19. So 0.95 to the 19, and I am going to get 0.377. So what I know is that in the year, 19 years after 2000, so in the year 2019, my population is still a little bit above 5,000, but somewhere in that year, so before 2020 and in the year 2019, that population dips below 5,000. So we can say, therefore, in the year 2019. That's my final answer. Now, we could have used this formula and plugged it in right here. The only reason I chose not to do that is because typing into your calculator, there's more chance for a mistake if you're typing all of this versus if you were just typing in 0.95 to the power of n. But whatever is easier for you to understand, I am okay with.